Hey, well, welcome back to our Aspire 101 ETS Electrified Transportation Systems course. Today, we are pleased to have two of our leading experts from Purdue University as our guest lecturers. We have Dr. Junjae Ching and Dr. Siva Sitharaman, who will both be speaking. Apologize for probably butchering your names. You can fix that all as you start up. Anyway, we'll be speaking on being closer and closing power transportation human loops. So with that, I'll turn the time over. We'll stay here to help guide, and as usual, we encourage participation, throughout the lecture, and we'll watch the chat for you. If any questions come up, we'll stop you and get those questions in. But it's all yours. I think Siva, you'll be starting. Is that correct?
I will be starting.
Okay.
Are you guys able to see my slides?
I do. There you go. Yep.
All right. Yeah. So I'm very excited to be here. Actually, to share some of the research that I have been done with Siva and within Aspire and beyond over the past year, or maybe a little bit longer than that. I think the overall topic is about the nexus between the transportation system and power system, really trying to think about you have the power system, transportation system, and human users, and how are they going to be connected, and how can we potentially close this loop by leveraging the coupling between them and trying to optimize things. So that would be the high level idea. So let me start with a motivating example. This is actually more or less a personal example. So this is about morning commute. So every day I wake up, I use electric kettle to boil hot water, microwave oven to prepare breakfast at home. So I'm using electricity at home. After that, I'm going to drive an electric vehicle from home to work. In that process, I'm contributing to the urban traffic and maybe contributing to traffic congestion as well. So after I arrive at work, I'm going to use a workplace charger to charge my electric vehicle. And I'm going to start to use electricity at workplace. All right, so if you really think about this process, that I drive an electric vehicle from home to work, that means three different things. It means a vehicle flow. My car get relocated from home to work. It means some energy flow. If you really think about energy stored in the EV battery, for us who work on power systems, sometimes we'd like to think EVs as batteries on wheel, right? So we have all these batteries, and we are thinking about how can you potentially leverage them for the grid purpose, different grid services. But eventually, when this EV driving on the road, one way of thinking about them is they are really large batteries so moving around. So there's some energy flow associated with that. And there's also a user flow. I myself get relocated from home to work. And as a byproduct of the user flow, because I get moved from home to work, so originally I was using electricity at home. After I arrive at work, I'm using electricity at work. So that results in some relocation of electricity demand as well. So that is this arrow. So the process that I drive an electric vehicle from home to work really means three distinct type of flow, but they are so tightly connected with each other. So effectively, you can say this is one flow. And if we want a name for it, it can be an electrified traffic flow. And the central thesis of today's talk and a lot of work that we have been working on is really, can we nudge or potentially optimize this electrified traffic flow? And by doing that, can we think about to improve the performance of the electric power grid of the transportation system, of the systems that are tightly connected to this electrified traffic flow. So in the rest of today's talk, we are going to go through three examples. The first example is about workplace charging. It's thinking about, can we come up with some time-varying charging prices or tariff that help us to jointly optimize the performance of the transportation system together with the power system. That's the first example. The second example is about electrified shared fleet. So we are thinking about Uber and Lyft vehicles. They start to transition to electric vehicles. Can we use this fleet to not only provide transportation service, but also provide electricity service? And after that, I'm going to transition to Siwa, and Siwa going to explain the third example, which is tightly connected to a major research effort within Aspire on electric roadways. And there, our question is that if you have a bunch of electric vehicles driving on electric roadway, how do you design the controller for these different vehicles, which vehicle should get a priority and so on and so forth. And there, again, transportation and power tightly coupled with each other. So I think Siwa will also explain a little bit more about the modeling of the electric fed traffic flow and thinking about the modeling of the coupling of the two systems as well. So with that, let me start with the first example. This example is about workplace charging. So, for people who actually come from transportation engineering background, this picture and the setting should be very familiar with you. But if you are not, I'm going to explain the basic to you. So the starting point is actually very famous and celebrated model for morning commute in transportation engineering. It's referred to as a Victory's bottleneck model for morning commute. So here in this picture, I have a bunch of blue text. For the moment, forget about the blue text. So let me simply explain this classical model for the moment. And the model is very simple. You have a population of commuter, a bunch of guys, and then you have a very simple transportation network that only have two nodes. There's a home node, there's a workplace node. And everyone want to go from home to work. So this is for morning commute. And the only way to go from home to work, they have to go through a traffic bottleneck. And by saying it is a bottleneck, it means that if everyone decide to leave home exactly at the same time, well, they will have to queue up at the bottleneck. So there will be traffic congestion. You will have to wait in the queue. So, people will not be happy. So the conventional wisdom about this type of model, and that's actually our day-to-day practice as well, if you a part of morning commute traffic, is that you want to decide your departure time in a way somehow to beat the traffic. So you're thinking about, oh, maybe at 8:30 there are a lot of traffic, so maybe I want to leave home maybe a little bit early or a little bit late. So essentially what you are doing is that you are trying to trade off this traffic congestion, so how long you have to wait in the queue, with the potential cost or disutility of being too early or too late for work. Right, so that is the classical Victory's bottleneck model. And what we are trying to do here is simply we start to think about, let's say people start to drive electric vehicles. What's going to change? So here we are assuming people are driving electric vehicle, and we are start to consider that you are going to have workplace charging. Then essentially there are a couple of new elements that we're going to consider in our model. One is that the people are going to make a charging decision, whether they want to charge at the workplace or not. And there might be some charging costs, whether people decide to charge at the workplace or not, depending on the cost of charging at the workplace. And finally, depending on how, when people are going to arrive at work and whether they charge at the workplace, you can think about this notion of aggregate charging load profile. So think about at the workplace, you have a charging station, you have a bunch of EV arriving at the workplace, people start to charge, but take the point of view of power system operator. He's going to see this small node in the power network that's going to aggregate a bunch of charging load. So by the end of the day, power system operator will see this aggregate charging load profile. And an ideal case setting will be, for example, you want to have relatively low electricity system costs. You want to have a charging profile that is relatively easy for the power system operator to be able to serve. For example, you can have an aggregate charging load profile that match nicely with your solar generation profile. That would be just one example, right? So that will be the new considerations from high level. So let me actually try to provide a little bit more detail and go through some of the model details so that you start to see a little bit lower level, but I'm not going to go down to the full mathematical detail. At least you get some detail in terms of how this model working, the thinking process behind the scene of this work. So the starting point, let's actually start to think about the status quo without EV. So again, this is a standard bottleneck model. But let's think about a single user's decision. So how are they making the decision about when do they depart for work? So for the moment, we don't have the charging decision yet. So we're talking about non-EVs. And in the setting, everything is straightforward. So by the end of the day, people care about, well, a couple of things. So one thing is the arrival time, because you want to arrive work on time. You don't want to be too early. You don't want to be too late. So arrival time will simply be their departure time, plus how long you will have to wait in the queue, and plus some fixed travel time. So, as typical is done in this literature, we can just assume that to be 0. That's not going to impact the result at all. But the most important thing will be the congestion delay, how long you have to wait in the queue. And this congestion delay is something that couples the decision of all the people who is going to travel on that route, right? So if everyone leave the work exactly at the same time, the congestion delay of everyone going to be very high. Whereas if this, people's departure times will spread around, the congestion delay will be relatively low. And the departure time is something that you can decide yourself. This is completely individual, while the congestion delay really depends on the population's overall decision. So this is the first thing that's about departure time. And then everyone, from a transportation engineering's perspective, there is this notion of travel cost. And the travel cost for an individual will simply be the sum of the congestion delay cost. So if you have to wait in queue for X number of minutes, we simply multiply this time with your value of time that convert this to some sort of dollar value. That will be the congestion delay cost. That will be the first term. And then plus the second term, that will be the schedule delay cost. And here the idea is that everyone wants to arrive at work. All right, yeah. So everyone want to arrive at work at some ideal arrival time T star. So if people's arrival time is before the ideal arrival time, it's not ideal. So there is some disutility. So you can see there's some piecewise linear function, and the cost increase if you are too early. The more early you are, the higher the cost you will be. And if you're late, well, there will be a higher penalty rate. That will be the second part of this piecewise linear function. The basic notion is that people want to arrive at the ideal arrival time, and depending on how early and how late you are, there will be some penalty. Right, so this is for the case that everyone drive a non-EV, so we're not thinking about EV for the moment, and they're simply deciding when they are going to depart for work. So what's going to happen, and what's going to be the notion that we use to characterize the result of this system, is that everyone going to make their decision. But at the end of the day, after they make this decision day by day, they are going to sort of settle down some equilibrium decision. And this decision will simply be, okay, I am going to depart for work at this particular time. And after everyone make this departure time decision in the equilibrium, what's going to happen is that we can look at this entire population. At any particular time instance, this is what this diagram is trying to show. Here, x-axis is different time, and the y-axis is the cumulative departure and arrival. So departure is a red curve, and the arrival is a blue curve. And the red curve, for example, tell you at any particular time, how much percentage of the user have already leave for work. And what you can see is that the slope of this cumulative departure curve in the beginning is relatively high because people prefer to be early than late. All right, so they don't want to be late, so they are going to depart for work at actually a higher rate than this blue curve. And this blue curve actually is the processing rate of the bottleneck. So what's going to happen is that people are going to arrive at a faster rate, and people are actually going to queue up at the bottleneck. So there will be some congestion delay. So after some critical time, people start going to reduce their departure rate because, starting at that point, people, if you if you depart after that point, you are actually going to arrive late for work. So what's going to happen is that they are going to depart at a slower rate. So that's the second part of this piecewise linear function. And overall, what's going to happen is that during this entire interval, when people travel, when people depart for work, there will always be traffic congestion. Actually, we can show that the total congestion loss is proportional to this gray triangle that I'm showing up here. So basically, the area of this gray triangle going to tell you how much congestion, the total congestion incurred by everyone, so the entire society. And the ideal case will be where you actually want to minimize the area of this gray triangle if you are a transportation engineer, if you care about the cost of the transportation system. And actually, in principle, this is possible. Because what you can potentially do is that you can line up everyone one by one, exactly make them to depart at the rate of the processing rate of the bottleneck. So actually, in principle, you can have this red curve overlap with a blue curve. In that case, you can eliminate traffic congestion. And in transportation engineering, people have demonstrated this is indeed possible with some, for example, some tolls, some dynamic tolls. So depending on when you go through some bottleneck, you actually have to pay some toll. In principle, you can achieve this ideal case, there's no congestion delay. All right, so this is for the case without EVs, and this is more or less the status quo. Now let's take one step further. Let's start to think about when people switch to electric vehicle. One of the key modeling elements that we have to understand is how people make the charging decision. So here, to make our model a little bit more realistic, we actually consider a case that we have, this population of commuters, they have heterogeneous valuation for the charging service at work. And the basic idea is that because different people have different options for charging, not everyone have to charge at the workplace. Some people may prefer to charge at home place. It's easy for them to charge at home. Some people may not even have the home charging option. So the way that we model that will be for an individual indexed by I, there will be this valuation, theta I, and this is going to follow some distribution. Some people will have high valuation for the workplace charging. Some people will have low valuation for people only have the option of charging at the workplace. Valuation of workplace charging going to be very high. So the idea is that for everyone, there's going to be different valuation that's described by this distribution function f. And then for everyone, the decision about whether they charge at the workplace or not, denoted as xi, should be very simple. They either charge or not charge, and they are going to charge if their valuation is higher than the charging cost. So here I'm saying, okay, xi is this indicator function, and indicator function is something very simple. It should be equal to 1 if this condition that I put in here is true, and it's going to be 0 otherwise. And this condition is simply if the valuation is greater than the charging cost. Here I'm putting a very general notion here, saying that the charging cost could depend on departure time. So I'm saying, okay, the charging service provider could ask the EV owner to pay a different amount of charging rate depending on when they arrive. In general, this is possible. Perhaps in the status quo, most of the charging service provider, they are asking for a constant price, but sometimes, if charging demand is very high, it is quite rational for the charging service provider to increase the rate or decrease the rate depending on charging demand. So in principle, this charging cost could be a function of the arrival time. So we allow that possibility for the moment. And then now if we want to model an EV driver, not just an ICV or internal combustion engine vehicle driver, their total travel cost, this commuter cost, will not only include the travel cost component, which is what we explained here, but also include this charging cost component. That is simply this net charging cost that is displaying here. That's going to be the charging cost, the amount of money they have to pay to the charging service provider, minus the valuation they get from this charging service. So that will be the total commuter cost, travel cost, plus the charging cost. All right. And then, in this new model with EVs, everyone have to make two decisions. One is when do they depart, and second will be whether they charge or not. And, that essentially is the two of the three new model elements that we have in this model. The last one is really about the aggregate charging load. What power system operator by the end of the day will see at that particular charger after people decide their departure time, which result in a different distribution of arrival time, and after people make their decision about their charging as well. So for us to model the charging load, well, actually, we don't have to introduce all these assumptions, but for the sake of the simplicity of this talk, let me introduce a bunch of assumptions so that you can see the most intuitive case, what's going to happen. All right, so for the moment, we are going to assume everyone going to start to charge upon arrival. So if they want to decide to charge, they are not going to play this game of they arrive at a time and then they wait, let's say an hour, and then go back to the charging station and then connect and charge later. So let's say if they want to charge, when they arrive, they are going to charge. So that's a simplification that we're making for the moment. And second is that we're going to assume all the charger at the workplace have exactly the same power limit. So all the charger are identical, and we also assume all the EV have the same energy need. This assumption is completely not needed, but for the moment, for simplicity, let's just make that assumption. And then for the status quo, let's think about the setting that the charging cost actually does not depend on time. So it's a constant, some pi naught. And let's say for the moment that this charging cost is actually relatively low, so everyone would prefer to charge at the workplace. Just to give you some idea of how this aggregate charging load is formed. So if we form this three assumption, everyone going to charge, and then if someone charge, their individual charging load will be this rectangle that I'm showing up here. Of course, if you actually understand the power consumption of the chargers and so on and so forth, it's not going to be a rectangle. And in practice, we can model arbitrary charging load. But here for simplicity, let's just assume the charging load is going to be this rectangle. The starting time of the rectangle going to be the arrival time of this particular driver. And the height of the rectangle going to be the power limit of the charger. And the duration of the rectangle will be the total energy demand of this particular EV divided by the power limit. All right, so this will be the charging demand of an individual driver. And you already see this charging demand depending on their transportation or their departure time decision, because their departure time going to depend on, because their arrival time going to depend on their departure time and how long they wait in the queue. So, but how long they wait in the queue will depend on the overall traffic pattern, which depend on the departure time of the entire population. So this thing essentially tightly couple the transportation or the departure time decision with the charging decision and the charging load the power system operator eventually will see. But for the moment, this is an individual load. Now, if you start to think about everyone will have such a load, then what's going to happen is that, well, different people are going to arrive at different time. So what you're going to see is that you're going to stack all these rectangles one by one, depending on when people arrive. So at the end of the day, you can calculate this aggregate charging load as a simple function of the arrival time of the overall population. So you can do some integral and you can calculate that out. Here, I'm not going to bother you with the math and the exact formulation. And this statement is also true even if you have a non-rectangular load shape. Now you can put a different load shape, but then when people start to charge, again, depend on their arrival time, and therefore you have this coupling between the transportation or the travel pattern and people's charging behavior. All right, so this is how the aggregate charging load will be formed. And now let's think about this status quo with EVs. Here I'm simply saying, let's assume all the charging service provider charge a constant charging cost. And the constant charging cost is relatively cheap. Let's say, for example, some of the large tech company, they even provide free charging to their employees. Everyone charge at the workplace. What's going to happen? So here I'm showing exactly the same figure I was demonstrating a few slides early, except that I'm starting to put something related with the charging load and the electricity system cost. And here for simplicity, we are actually consider very, very simple electricity system cost. So the idea is that we want to match the EV charging load with a solar generation profile. So we consider a setting where you have a large amount of solar generation after sunrise. And the simplest setting will be, charging is cheap or essentially free before sunrise, and charging after sunrise, the other way around. Charging before sunrise is more expensive, and charging after sunrise will be cheaper. All right. So if we take this very simple electricity system cost, essentially trying to match the charging load with the sunrise time and the renewable generation, then what's going to happen for the status quo is going to be, well, people are still going to travel more or less the same way they traveled before. So you see the same red curve, the same blue curve that I have drawn in the previous slide. The only difference is that this yellow triangle actually going to be something scale with the additional electricity system cost, the suboptimal electricity system cost. So essentially, this part is trying to say, okay, in principle, you can potentially make people to charge after sunrise. But in this setting, because people actually arrive before sunrise, and because also the charging cost is cheap, they end up charging before sunrise. In that case, the entire electricity system incurs some additional cost. So this is actually non-ideal. So if possible, we would like to eliminate this yellow triangle, or maybe move this entire departure or arrival time after sunrise. All right, so that's more or less the status quo. What we are really trying to do here in our research is that we want to think about, can we play with the pricing of the workplace charger? So if people arrive at work at 8 o'clock, maybe you see some price. If they arrive at 9 o'clock, maybe you see some different price. Maybe there's some discount depending on how do you arrive at work. We want to understand, at least on a conceptual level, what is the potential of doing something like this? So if you want to think about this process, what's going to happen is that you are going to have a bunch of users. They are heterogeneous, so they have their own payoff function, their cost function. That's a commuter cost we talked about previously, that they are also optimizing by making their own individual departure time and charging decision. And this payoff function going to impact and indirectly decide some transportation system user equilibrium. By the end of the day, everyone going to, at the equilibrium, everyone going to make their departure time decision, everyone going to make their charging decision at the equilibrium. And then I, as maybe a social planner, maybe I care about transportation system costs, maybe I care about power system costs, maybe I care about the sum of both system costs. But in any case, I can look at, at the equilibrium, given that this number of people are going to arrive at this time and so on and so forth, you have this entire distribution. You can look at the overall transportation system cost. You can look at the overall electricity system cost, and you can understand, whether this is good for the entire society. If you are not happy about that, what you can potentially do is that now you can play with your control knob here, and the control knob will be some time-varying charging tariff, different charging prices or discount depending on when people arrive, and that will in turn impact people's cost function, which going to impact the user equilibrium, which is going to result in a different transportation system cost and the electricity system cost. So overall, it's going to be a closed loop system where you change the charging tariff and hopefully impact the equilibrium and the performance at the equilibrium. So here, there are potentially different type of social planners. There will be people care about transportation system costs, primarily thinking about, transportation authority of some city, traffic manager, and so on and so forth. For them, if they have access to this control knob, effectively what they are doing is that instead of imposing some, let's say, time-varying toll, they are essentially trying to use EV charging tariff effectively as a toll. But this thing potentially can be more effectively than toll because you don't have to stop traffic, you don't have to, build a toll station, and so on and so forth. Everything is just through slightly different change of the charging cost or maybe some discount you give to the drivers. So that is for the purpose of optimizing the transportation system cost. Now, we can also potentially use this time-varying charging tariff to optimize electricity system costs. And there the notion can be potentially you want to reshape the aggregate charging load so that the aggregate charging load perhaps match with renewable generation a little bit better. So that, for example, if you're aware of power system problems, one of the major problems is, for example, the California duck curve, where, after sunrise, you get a lot of renewable generation, you have a lot of, the power system actually ramp down, and potentially you can use this type of incentive to make people charge at the right time so that the total electricity system cost can be a little bit lower. All right, so we can also think about we are a social planner who care about both the transportation system cost and electricity system cost. In general, that is possible. And the question will be, how do you jointly optimize both systems at the same time? All right, so, well, this can be written as a actually quite complex mathematical optimization problem. And here I'm not going to bore give you all the details on, all the mathematical detail can be quite troublesome. But let me actually give you a very high level formulation. And the idea here is that you are trying to decide this time varying charging tariff, this pi. And the hard thing about this pi is that this pi is a function. Think about different arrival time, people are going to get different discount or different price for charging. So it's a function that map a real number to a real number. Given some pi, we have this notion of user equilibrium. And given the user equilibrium, we can evaluate some social cost metrics. Think about some electricity system costs, given the aggregate charging load at the user equilibrium, or the transportation system costs, think about the traffic congestion and so on. And you can also optimize the sum of both system costs. In any case, you are going to have some social cost metrics that you want to optimize. So this optimization, even though I'm writing down at an extremely simple form, is actually very challenging mathematical optimization because this decision variable that you are optimizing here is a function. So, in mathematical terms, it's an infinite dimensional optimization. You don't really have efficient algorithm. You cannot go and find a solver to solve this type of optimization. And the second issue is that if you put an arbitrary tariff, just the problem of characterizing the user equilibrium is quite challenging, let alone optimizing the tariff and optimizing the user equilibrium. So this is effectively, if you want to solve this for a general system, it's a very, very hard mathematical optimization problem. We actually are able to identify some interesting theoretical technique for solving this type of problem. So essentially we get some lower bound. And the basic idea is that, in this optimization, we are trying to come up with some incentive and people look at the incentive, make their own decision. So it's like a decentralized optimization. People still make their own decision by looking at the prices for charging. But we can actually get a strictly better performance for this, or at least lower than equal to the optimal performance of the social cost by a centralized social cost minimization. And the idea is that instead of coming up with this tariff and make people to make their own decision, let me just become a dictator. I tell everyone, hey, you have to depart at this time, you have to charge at that time. And then if I solve that optimization, the cost for that optimization going to be strictly lower or less than equal to what you see here. So that will be a lower bound. Now, if I can design a charging tariff that achieves exactly that lower bound, I have proved that this charging tariff is optimal. So that is actually the way that we are going to solve the problem. So without giving you too much mathematical detail, let me actually give you the results in graphs. So it turns out what we can do is that we can design an optimal charging tariff that achieves the social optimal performance if we only optimize transportation system cost. That is a graph I'm showing here on the left. And what you can see is that I completely eliminate the gray triangle that you have saw previously in the figure, and that's corresponding to traffic congestion. So I can create this EV charging discount exactly in a way to make people to line up so that they don't rush, they don't go to the bottleneck at a rate faster than the processing rate of the bottleneck, so that you have the red line and the blue line overlap with each other and there's no congestion. So this is an ideal case for the transportation system. This is ideal for transportation, but it's not ideal for the power system because you can see still the power system is paying this actual electricity system cost, as you can see in this yellow triangle here. So it's not optimal for the power system. This is only optimizing the transportation system cost. Now I can design a different tariff if I only care about power system or electricity cost only. So that tariff actually is very easy to design. All you have to do is you essentially give people a discount, actually a lot of discount, if people arrive for work after sunrise. And in this case, everyone will essentially depart and arrive after sunrise, and they are going to charge after sunrise. And you can see in this case, there's no this yellow triangle. The additional electricity system cost is completely eliminated. This is the exact optimum for the power system. You perfectly match your charging load with renewable, with solar generation in this case. But in this case, it's not optimal for the transportation system. As you can see here, you still have the gray triangle, and you still have some traffic congestion loss, which is not ideal for the transportation system cost. The takeaway for the slide is that individual system costs can indeed be optimized with some tariff, with some EV charging tariff. All right, what about joint system optimum? Can I jointly optimize performance of both systems at the same time? So it turns out we cannot do that. And the way to understand that is that we can think about a centralized social cost optimum. So we are talking about the case that I'm a dictator, I tell everyone what they should do. And in this case, you actually get the optimum departure, arrival, and charging decision as demonstrated in this graph. Here, what's going to happen? You can see that the blue line and the red line, they are going to overlap with each other. So you actually completely eliminate traffic congestion. So that is ideal for transportation. And the interesting part is that you're actually going to make some people depart earlier than the sunrise time. And the way that you are going to make sure there is not additional electricity cost for these people who depart earlier than the sunrise time is that you are going to ask these people, even though you depart early, please don't charge. Now, if they don't charge, well, there's not going to be additional electricity cost associated with these early departures. That will turn out to be the centralized social cost optimum. Now, what we can prove theoretically is that this is, in general, impossible to do with some tariff. And it's quite straightforward for you to understand why this is the case, even though the proof by itself is not straightforward. You just think about people who actually arrive early, right? So if you want to encourage this type of behavior for people who arrive early, if you want them to not charge, the only way you can do that is that you are going to make the charging cost very high. Now, if the charging cost is high for people who arrive early, then everyone arrive early is going to decide to not charge. Now, if they decide to not charge, then what's going to happen is that these people will not see a time-varying incentive associated with their departure time. So what does that mean is that, these people essentially, they are not seeing any incentive. They are just going back to the status quo without incentive because they are not charging anyway, right? So what's going to happen is that they are going to actually depart at a rate faster than the processing rate of the bottleneck. So for this small chunk of people who are actually going to arrive early, you are actually start going to see some traffic congestion. And that will be suboptimal for the transportation system. And that is why this picture is impossible to achieve if you only have a electricity EV charging tariff. All right. So, so far, everything I've been talking about, they are quite conceptual, they are theoretical at high level. We're actually doing the same, trying to build all the practical complexity on top of that by looking through a number of extensions. For example, this joint social optimum is impossible with just charging tariff. Could you combine it with some transportation engineering knobs like tolls to potentially achieve this social optimum? That's one of the directions we are exploring. So far, we're actually assuming everyone is driving an EV. Of course, it does not have to be the case. We have some results of hybrid fleet where some part of the population is driving EV, some part of people are driving non-EV. And it's actually quite interesting that even though you may have a small EV penetration, because non-EV users will anticipate some behavior of the EV users. So at the equilibrium, there's two parts of the population, they're actually coupled. So there are actually some interesting questions over there. We're also thinking about combining this with a smart charging. So far, there's no control over charging people when they arrive. If they want to charge, they start to charge. What if you can do smart charging on top of this? We're thinking about more realistic power system costs, thinking about the spatial aspect. Right now, the transportation system and the power system network, they are extremely simple. What if you have a realistic network, different routes, how people are going to make their decision, how you're going to characterize the equilibrium, how you are going to solve this pricing problem. So there are a lot of exciting direction we are pushing and really trying to make this more realistic. All right, so this is a first example. Let me actually move on to the second example. And the second example is actually about electrified transportation network company. The idea is, we have Uber and Lyft. They are quite popular, where depending on where you are, especially if you're living in large cities, they are extremely popular. And they are actually in the process of transition to electric vehicle, because it makes sense for them to transition to electric vehicle, because they drive a lot of miles every day, and they drive in the urban driving environment mostly. So, electric vehicle turn out to be more efficient for this sort of settings. Uber and Lyft actually have programs to incentivize their driver to switch to electric vehicle, for example. And the high level question here is that now you have this Uber and Lyft vehicle. They are some sort of fleet controlled by some matching platform in some sense. So you can think about them as a platform that providing transportation service, but for people working on power system, what they see in terms of this is really a huge opportunity, because you have a lot of these EV batteries. They are not like exactly dispatchable, but they are more or less dispatchable. So you can make this EV battery go to different locations. So what if we can use this EV batteries to provide some electricity service to help the grid? Is there any benefit for doing so? Does it make sense for you to combine transportation service with electricity service? So this is a high level question we are trying to answer in the second example. So there are actually different type of potential electricity service that someone may come up with. For this talk, we're actually going to focus on a particular electricity service that we identified. We demonstrate with data that this is actually quite profitable. And this service is about demand charge reduction for large electricity users. So we are talking about commercial, industrial electricity users. And for people who are not familiar with utility tariff, this is for commercial and industrial electricity user, or C&I user. Actually, for their electricity bill, usually they consist of two major components. There is a usage charge, or volumetric charge, or energy charge. They have different names, but the basic idea is that by the end of the month, the utility company going to calculate how much electricity that you have used during the entire month, and based on this total kilowatt hour of electricity consumption, and there might be different rate structure, but essentially based on this total electricity consumption, they multiply that with some rate for each kilowatt hour of electricity consumption, and that will be the energy charge or the usage charge. And this is something calculated based on total kilowatt hour of electricity consumption. And for residential customer, like in your apartment, you are going to see this part of the bill. Now, for the commercial user, they have this additional part of the bill that is a demand charge. And this is something that actually calculated based on maximum energy consumption over the month. So how is that calculated? Well, what utility company will do, where they have the smart meters, what they do is that they can identify, for the entire month, what is your maximum electricity consumption in any of the 15-minute metering interval that they have collect data on. So if we denote that with Q, that's going to be some number with a unit kilowatt hour. That's the energy, electricity that you use in that 15 minutes. And then what the utility company does is that they're going to convert this energy number into a power number. So they take this kilowatt hour number divided by the length of the interval, which is 15 minutes, which is 0.25 hour. And that will be the maximum power that electricity utility company have measured you. So they were going to count you based on this number. They are going to assume this is your maximum power over the entire month. And by the end of the month, they are going to calculate this demand charge number by multiplying your maximum power. They calculate it in this particular way with some rate. And here I'm putting some typical number. I think this number is coming from some California utility company's tariff. So energy charge every kilowatt hour is on the order of 10 cents all the way to 20 cents. In this case, it's 17 cents. And demand charge for each kilowatt, this is $19, close to $20. So this rate is much, much higher than the energy rate. Even though this is just one-time thing, by the end of the day, you just have one interval get this demand calculated and demand charge calculated. But because this rate is very high, for large business, large commercial and industrial electricity users, in their monthly bill, demand charge can account for 40–15% of their electricity bill. This is a very significant component. of their electricity bill. And here I'm just giving you a numerical example. What's showing here on the left is the energy consumption time series. X-axis is an index of different metering intervals. Y-axis is a measured energy consumption. And as you can see, what we are doing here is that we can calculate the total energy consumption. That is the energy column in this table, the Q that you calculated, some kilowatt hour number. And you can also calculate the demand number. That is the peak of this blue curve. You can see it's around 18, and then you divide by 0.25, effectively multiply that by 4, you get 17.3. That will be the maximum demand the utility company measure. And one of the interesting observations is that if you can actually reduce the energy consumption of this user just in that critical metering interval, by actually just a small amount, you think about reduce the energy consumption of that user by 4.1 kilowatt hour in that metering interval. So that essentially make this meter energy consumption get into the red curve instead of blue curve. Your impact to the energy charge is minimal. You reduce energy charge a little bit by $0.7, but you can significantly reduce the demand and significantly reduce the demand charge. In this case, just by reducing the energy consumption by around 4 kilowatt hour, you help this customer to save more than $300 in demand charge. So this is quite significant savings. And the interesting observation is that all you have to do is reduce energy consumption in 1 metering interval. All right. So the overall idea that we want to do is we are thinking about, can we use Uber and Lyft vehicle to do that? Can we use a matching platform like Uber and Lyft to potentially provide the service? All right. So if we want to set this up, you can look at the figure on the right. We have this matching platform. On the supply side, you are going to have a bunch of EV drivers and the EVs. And on demand side, you are going to have a bunch of commercial industrial electric users. Here I'm putting a grocery store, which is a perfect CNI user. And here we are making an assumption that this commercial and industrial electric user have a bi-directional EV charger installed. So if an EV comes to the location, they can actually discharge its EV battery, provide some energy to this electric user and help them to reduce the metered energy consumption, the energy consumption seen by the utility company. So in this case, how the business work, where simply, for this user on the demand side, if they anticipate, okay, they are going to have this peak metering interval in some time, they are going to request some EV to come to its location. The matching platform going to identify a nearby EV. The EV driver will get to the user's location, connect to the bidirectional EV charger, and discharge its EV battery for the time period the user requested. And as a result, the metered energy consumption of that metering interval going to be reduced and demand charge will be reduced. All right. So if you really think about this as a business model, this thing only makes sense under a couple of quite important assumptions or conditions. So this is an example of sharing economy, and sharing only makes sense if, for example, different users are going to request service at different time. So for example, if you're running this service for, let's say, 100 users, but if all the users making their requests at different time, then there's no point of sharing, right? So I'm sorry, if all the users making requests exactly at the same time, then there's no point of sharing because all of them are requesting at the same time, and you have to have different EV to serve each of the users. So for 100 of users, you will need 100 EV. There's no sharing. You need a lot of EV, a lot of capital to actually procure the EV and so on and so forth. So this thing only makes sense. You have a nice case of sharing if people are going to make requests at different time, and people are going to make requests at different time only if their maximum energy consumption in the entire month, so their peaks are temporarily dispersed. So they peak at different time, and then they are going to make requests at different time. So that's one of the very important conditions that we have to check. And the second condition, like any business model, you have to make sure the revenue of the business need to be able to cover the cost. And there are different sort of costs. For example, battery degradation, bidirectional charger, wage, and the benefit of the EV drivers and so on. All of this cost money. So somehow the revenue of the business need to be able to cover the cost. So what turns out is that we did a very extensive data analysis. We demonstrate both conditions actually hold. So this business actually makes sense. So for the first condition, that the peaks of different user tend to happen at different time. We actually look at the temporal statistics of different users. This is for 100 users over some data set. For this case, the metering interval is 30 minutes. We look at this for different months. There are 70 months in the data set, but the plot is for 1 month. Again, x-axis is the index of metering interval, y-axis is the number of coincident peaks. That's essentially you count the number of users who's going to have a peak, their monthly peak in that metering interval from each metering interval. The most important number you read from this figure is the maximum of the y-axis. You can see the maximum is 2. What does that mean? That means the maximum number of coincident peak is 2. That means at any time, you have at most 2 users making requests at the same time. So this says if I want to run this business with EVs, and if I don't worry about time that needed for EV to go around and recharge and so on and so forth, I just need 2 EVs to serve this 100 users. Now, if I actually account for the time for recharging, you multiply 2 with some factor, but still take away is a small number of EV can serve a large number of users. So indeed, the peak of different users happen at different time. And we also did a quite extensive cost and benefit analysis, which showed that the revenue from demand charge reduction on the saving for the customers actually is much more than what's needed for you to pay for the bidirectional EV charger. You can also pay the EV driver a similar salary as Uber and Lyft are paying, actually much higher. I think actually about twice the salary. So EV driver, they can make their decision whether they provide this service or just drive for Uber and Lyft. So, cost and benefit also check out, the thing actually makes sense. And actually, the next idea is really think about, okay, you can provide the service, electricity service, use EVs. Do you really just want to provide the service as a standalone service, or potentially you can have Uber and Lyft provide them together? You can have transportation service combined with electricity service. So for this, actually we'll show at least on high level, it makes sense. And because there's some nice complementarity, there's a temporal complementarity. The request of this demand charge service actually happened during middle of the day, and the request for Uber and Lyft service, this from real data, have this dual peak pattern during the middle of the day. There's this valley can be potentially filled by this electricity service. And there's also a very nice notion of spatial complementarity, really depending on where other businesses are located. If you can send this EV to the parking lot of this business and provide this electricity service, it help you to essentially reduce some of the idle vehicle on the street that help you to reduce congestion and so on and so forth. For the sake of time, I'm not going to get into all the details, but there's also a spatial complementarity. So on high level, it makes sense for you to combine electricity service together with the transportation service. And then what we did is we are trying to formulate a mathematical optimization problem. We're thinking about the problem of a platform like Uber and Lyft. They want to maximize their profit, and they cannot directly control where the drivers go. What they can do is that they can play with the prices. A different location for different service, they can have different prices. So we write down this optimization as a spatial pricing problem, essentially trying to come up with different prices of different location in the transportation network. Driver can make their own decision of where they go, which service they provide, and where we are trying to characterize the market equilibrium. And then we are trying to see, how do we tweak different prices that will help the platform to maximize profit at the equilibrium, consider the profit of both the transportation service and the electricity service. So what we can demonstrate here is that actually, if you do this optimization, not only you can help the platform to make more money, certainly, and second is that actually there's some complementarity. Because of the complementarity between these two different services, when you combine these two services together, there's some synergy, there's some additional benefit that you can get. So you get more profit than having separate fleet providing separate services. And in addition, it also helps the Uber and Lyft vehicles to essentially get off the street because they get into a parking lot to provide electricity service that help reduce the congestion and help the urban traffic congestion, especially during the middle of the day. So what's trying to show here is essentially the overall sort of spatial distribution of pickup and drop off. And as you can see, if you compare this figure with this previous figure, we have a lot of red area, which is going to correspond to more cars get into this area, then cars go off this area. Now, if you have a lot of Uber and Lyft cars getting into this area, not getting requests, you're going to end up with a lot of congestion. And as you can see with our optimization, we can eliminate a lot of red areas. So this is a win-win both for the platform and for the overall society in terms of traffic congestion reduction. All right, so that's everything that I'm going to have. I think I'm going to hand off to Siva, and yeah, I'm probably going to answer all the questions towards the end.
Okay. Thank you, Junjie. Kind of continuing on this theme of optimizing the transportation, energy, and human nexus. The last example that I'm going to talk about is one of electrified roadways, and this is something that's central to what Aspire is doing. So this is a joint project where we've been trying to look at this whole system. How can we model the behavior of EVs? How is that going to affect the transportation network, or how is transportation congestion going to affect EV charging behavior on electrified roadways and so on. So the system that we're considering here is pretty simple. It's kind of idealized. Assume a highway segment where we have a bunch of vehicles that are driving down the segment, which are EVs. Now, the key idea in dynamic wireless power transfer is that these EVs can also charge as they are driving. So we assume that that is going to be powered through some sort of a microgrid, which is could potentially have things like renewables, like solar panels could power this system, but also there is a substation where it's connected to the main grid for grid support. So this is kind of dual in a sense that there is a microgrid, but it's also grid connected. So there are three kinds of flows to consider here. The first one is that the EVs are going to be driving along this road as if it were a normal road, which means that there could be a lot of different traffic flow patterns. You could have free flow, you could have congestion, you could have various waves of shock wave type congestion patterns, lots of different behaviors that are quite complex from a driving perspective. The second part of it here is that we are basically using this microgrid to power the wireless power transfer coils that are embedded into this road. So there is a power flow that is going in that's coupling this network. And then these are going to be received by receivers that are placed in these electric vehicles. So there is a power flow that's coupling this traffic flow here. The last thing that we have here is there is some sort of onboard communication that is necessary in these EVs to be able to meter this consumption at the end, where you'll have to see how much energy has been consumed by any particular EV for billing and other purposes like that, and also in terms of when they're entering and leaving and so on. Right. So the key idea here is that in medium to heavy duty vehicles, we can imagine that these EVs will be charged as they are driving. But the challenge here is that the transportation dynamics are complicated, and also EVs can arrive or exit this segment at various different times, right? So the amount of time that an EV is going to be active in a certain segment is going to be difficult to forecast. So this is very different from a stationary charging perspective, where if an EV arrives at a charging station, we usually assume that we know what is the charging demand going to be and how long they're going to spend there. So this is fairly, you can estimate this quantity fairly reliably. However, in the case of electrified roadways, this, as we will see, is going to depend on various different things, including, there could be exits along this highway, and more importantly, traffic congestion patterns are going to integrally change how long the EVs are going to spend on this segment and how much charging they're going to need. Right. So the key idea here is we want to minimize the cost of procuring energy from the grid while serving the charging needs of these EVs. However, this is going to be a complex optimization problem, like I said, because we need to understand when an EV enters a particular segment here, that is an electrified roadway segment, we need to already be able to understand and forecast what is going to happen in terms of the driving behavior. So how are they going to drive, how long are they going to spend on the segment, and how much charging they need. Okay. So when we look at the model itself for the electric vehicles, there are there's basically two types of things. The first one is that there is an amount of energy that's going to be used directly for propulsion through wireless charging. So there for vehicle propulsion, as well as auxiliary systems on board, for example, onboard communication, onboard electronics, so on. The second thing is battery itself. So the EVs, if you look at medium to heavy duty vehicles, these are basically carrying large batteries, and these would also be charging as they're driving along this road. So in total, when you look at the amount of energy that is going to be consumed by an EV driving on this road, it basically is the sum of this, the amount that is being used to charge the battery and the amount that's being used for propulsion and other auxiliary systems. When we look at the grid side, we are using a very simple model here, where we're looking at the costs incurred by the grid. The total amount of energy that is going to be served to the EVs needs to be met by some combination of the local generation available at this microgrid, which is in the form of solar panels, we're assuming here. You could also have a wide variety of other options here. There is also the part that you're getting from the grid, which is coming from the substation. So this is the grid cost, and it comes with a certain cost of acquiring energy from the grid. So the total of the locally generated energy through solar energy and the energy imported from the substation, it should be sufficient to meet the wireless charging demands of EVs driving on this road. So when we look at the optimization problem from the grid perspective, what we're trying to do is to, over a time horizon, capital T, there is a total cost which is basically going to be the net power that is procured by the grid, from the grid. So that's going to be the difference of the amount of energy that's being transmitted to the EVs minus the solar power that's already generated on site in the microgrid. So this is going to be the net power that is going to be procured from the grid, which comes with a certain cost function, C, associated with it. Now, for simplicity, we're assuming that this cost function is stationary, so there is no time change in terms of this particular cost for grid, for procurement from the grid. Okay, so the grid, so the microgrid itself is trying to minimize over possible, power that needs to be transmitted to the EVs, this net cost over a certain time horizon. Now, there are a couple of constraints that come in here. The first one being that each vehicle, of course, has a certain minimum and maximum energy limits, which are basically determined, the minimum is 0, and the maximum is determined by how much the vehicle is able to receive. And there is also some constraints where the amount of energy that is being consumed by an individual EV is going to be related to both the two parts of the energy consumption that we talked about. One is for the propulsion and auxiliary systems, and the other one is basically going to be dependent on the onboard battery. So it's going to be at each time interval, it's going to be the difference between the current state of charge and the next state of charge. So this is what's going into this right-hand side here, the capital WI, and this is going to be determined by the battery dynamics of the EV. So when we look at this optimization problem, There are several complexities. Even if you assume a perfect transmission where we're ignoring any sort of losses from the energy, losses between the transmission of energy to the of wireless power from the roadway to the EV, if we ignore the transmission receiving systems losses, even then this problem still has a lot of complications. The first one is kind of simple. In the cost function here, we have this solar generation from the microgrid. So we need to understand how this is, what we can expect to generate over this time horizon. So at at the start of this horizon, when we're trying to optimize over this entire time horizon t, we need to be able to understand what solar power is going to be generated. The second slightly more complicated problem here is that the amount of energy consumption by the EV depends on a number of different factors, right? So the first one is the vehicle propulsion bit, which is basically just talking about how much energy it's going to take to power the vehicle through this particular roadway. And the second part is the battery charging. So when you look at this, these two parts here, both of them essentially depend on the amount of time that this EV is going to spend on the roadway, which depends on the traffic conditions. So if this is going through the whole section really fast, or is it going to be stop and go through this entire section, and all of that is going to change both of these quantities. The other thing that's going to matter is the state of charge with which this EV is entering the roadway. And the state of charge with which it's going to exit is obviously going to depend on the amount of traffic as well. So all of this essentially makes this problem traffic dependent, which means that we need to be able to consider the dynamics of the transportation network in this optimization problem. So this is a very, very tightly coupled problem where the cost of minimizing energy for the microgrid that's powering this electrified roadway is integrally coupled with the dynamics of driving on this roadway. Right. So when you look at an optimization problem with this structure, there is some theoretical work basically showing that the optimal charging profile is to basically maintain a certain constant net charge that is delivered to the vehicles on this section, right? So the net charge, of course, is the sum of that which is delivered to each EV. So this is as long as you maintain a constant net charge level, and that net charge level is such that it satisfies all these constraints here, and this kind of a profile would be optimal. And this kind of profile is called the valley filling profile. Now, the issue here is that even if we can compute this constant here, there is still the issue of how do we basically allocate this to the different EVs in the segment, right? Because this only says that the total sort of net charging level is if there exists a constant net charging level that satisfies this optimization problem, then that particular solution is optimal. That doesn't mean that we know how to allocate this to the different EVs. And the second part of it is, of course, how do we even find this net charging level? Okay. So these are kind of two issues here. And the way we will tackle this is that we will, to allocate this net charging level, what we're going to be doing is to consider the concept of laxity, which is basically the amount of time that the EV is going to remain on at any given time point. It's basically the amount of time that the EV is going to remain on this electrified roadway segment, minus the amount of time, the minimum amount of time that is needed to fulfill the particular energy requirements of that electric vehicle. So what we can do is that, so assuming we can somehow find this constant net charging target, we can basically rank all EVs by laxity. So basically the amount of time they're going to stay minus the minimum amount of time that's required to fulfill their requirement. And we start with the least to the most laxity EVs, and we will basically assign that as the order of priority, and we will then in that order we would basically deliver maximum energy to them until the total charging target is met, which is this net constant target. So the second part of this is, I said if there exists this constant net charging level, then this solution is optimal. So how do we even obtain this, right? So even obtaining this has a few different challenges. The first one, the main challenge here is that to obtain this thing, once again, we need to understand how long the EVs are going to stay on this road. What is the solar generation? We need to basically understand all sorts of information about the future data in this system. So here what we are thinking about is basically using some sort of a prediction method, where assuming that for a certain time window, a short future time window, we are able to predict these parameters. So once we're able to predict these parameters, we can basically solve for this constant net charging level by obtaining the solution to this optimization problem, and then essentially we can get this net charging target. So the thing is that if we have some amount of look ahead, we can basically solve this this problem, and we can show we'll show that this is actually quite close to the original solution. Now, if we don't really have a prediction, then what we can do is use historical data as a proxy, maybe a little bit of a historical time window rather than a look ahead time window, and then utilizing that to estimate this net charging target, and then be able to again allocate them using this least laxity first rule. So when we look at the results here, this is for an idealized segment where we have different windows of look ahead windows. So if we have a 5-minute look ahead or 15-minute look ahead and so on. What we're seeing here is that this this red line is basically the solution of the clairvoyant optimization problem that I showed earlier, which basically means that if you had all the information. This blue line is for limited look ahead, which closely matches this this profile. And even when we have no look ahead, basically this still matches this profile in the case of smooth free-flowing traffic. So once again, if you increase the look ahead window, we see similar results. However, this is the second case here where there's congestion is where we really start seeing the impact of the coupling between the electrified, the traffic dynamics in the electrified roadway and what's going to happen to the costs here. Now, when we look at this, the second case where there's congested traffic, it's you can see a lot of disparity between the optimal solution and this one that we obtain from the limited look ahead or no look ahead. It's still pretty good, but there is clearly a difference here, which is getting smaller as we increase the length of the look ahead window. So as we we can get, if we are able to predict future data with more and more confidence, obviously we can solve this problem much better. Now, here the issue is that when you have congestion like this, it's very hard to predict how long this EV is going to stay on this segment and so on, because predicting traffic congestion dynamics is its own sort of big problem in this literature. But assuming that you have a certain way to predict it, then we can do quite well in this setup as well. So the first thing that, so I just want to zoom in a little bit into how we can predict the number of EVs in this segment and how long they're going to remain in this particular segment. The first thing that I'm going to show is a data-driven approach. The second part that I'm going to talk about is a more analytical modeling-based approach, and I will discuss the benefits versus disadvantages of each of them. So the first one here is going to be taking past traffic flows, and then we want to kind of understand how many EVs are going to remain on this highway, when are they going to exit the highway, maybe some of them will even head off to stationary charging points. So predicting, so first of all, traffic flow, we can get historic data for the EVs on the highway. One of the things that we can do is to take registration data from the Department of Energy data set and then try to scale the traffic patterns that we predict by the registration data to get the number of EVs in the corridor. Now, the number of EVs sort of exiting the highway, we can basically get by, there is some, sorry. Yeah, so basically the number of EVs that are exiting the highway, again, we can predict by predicting the turning ratios using historic data for different locations as well as different time windows like peak hours, morning versus evening, and the holidays and so on. Right. So taking the historic data from a particular corridor, in this case, we selected the I-210 West corridor in California. I had a team of undergraduate researchers working with us here. This is called the ORSOL team. It's part of Purdue VIP projects here, where basically undergrads work with on research projects with faculty. This is also, collaborating with SAS, who provides optimization softwares and forecasting softwares. So a team of these undergrads, basically what they did was they got a crawler and then they wrote a crawler to basically extract a lot of data from the I-210 corridor, which is basically traffic volumes and different vehicle detection sensors over, at each hour over a long duration of time. And see if we are able to forecast the number of EVs, and basically the time that the EVs would spend in a particular segment can then be estimated from that. So here, basically, this is a purely data-driven approach. There is no model in here. It's basically fitting a lot of different time series models or neural network type models in to the data until we get something that's close to the actual traffic flow patterns that we are able to forecast. So in this case, eventually we went with some sort of a stacked model, which has a neural network plus time series, which has some lag terms, but also neural network architecture for forecasting, which turned out to be the best model. So if you actually zoom into this data set here and you look at the traffic flows of predicted versus actual, they do match quite well, but more importantly, we are interested in these particular segments. These are the congestion segments, so the morning commute, which is going to result in a huge peak, the lunch break, where there's a little tiny peak, and then the evening commute, which is also a sort of a different peak, and we're basically able to forecast all of this simply by using time series or neural network models from the data. Now, this team also they did a little bit of a visualization that I can that I'd like to share for a minute. Sorry, is my screen visible?
Yes.
Yeah, we're seeing the simulation run.
I think this is my screen, but we are playing this on my screen.
Okay, can you play it again? I'm so sorry.
Replay it?
Yeah,
Oh,
just replay it. Sorry, I don't know
okay.
why it's showing your screen, but okay. Yeah. So essentially, yeah, could you play the bottom one as well?
Okay. Let me try to play it on at the same time.
Sorry.
Okay, so yeah, let me just
Yeah, because it's not playing on mine. Right.
all right, I
Okay.
think both of
Yeah, thank you. Yeah. So basically, this is kind of showing this segment on the particular freeway, along with the different, along with the charging, patterns, the actual versus predicted. This is like basically time lapse where we can see on this road segment what's happening. The blue points here are actually stationary chargers, and it's showing the demand that we predicted for the stationary chargers as well, given that this is going to be the traffic flow on the freeway. Thank you. So going back here, basically, when we look at this this kind of thing, this does have close alignment with the actual and predicted traffic flows. And again, this is purely data driven. This is one way to kind of estimate what we're looking for. But when we're looking at an optimization problem like this, if we wanted to provide certain guarantees, then we may also want to explore an analytical model. So we've been also thinking about putting in a predictive model that is a little bit more explainable in here. So what we are, one of the ways to model these traffic flows is to consider some sort of a mass conservation model in the form of something like the cell transmission model of traffic, which basically says that if I have a particular segment of road, I'm going to break it up into little pieces called cells or links. And for each one, I have an incoming cell and an outgoing one. And basically, I have the sum of the incoming traffic flows equal to the sum of the outgoing traffic flows into a particular cell. We can also expand this to more urban settings by adding things like traffic lights, which would basically give a binary multiplier to these flows. So when you think about this as a graph, basically what we're going to be writing is dynamics for the density of the vehicles or the number of vehicles. Basically, the density is the number scaled by the length of the cell. And if you choose the length of the cell such that a vehicle cannot cross more than one cell at a particular time interval, then basically you can simplify this model quite a bit. So using the change in the density of vehicles in a particular segment here, so we basically break up this roadway into a bunch of segments, and the change in the vehicle density is the inflow minus the outflow, and the outflow can be controlled by a certain control input, which can be traffic lights or ramp meters or things like that. We can also add in some uncertainty into this model that we can quantify once we fit this model. And basically this kind of a model is what goes into these inflows and outflows is basically two types of things. If traffic is free flowing, then the inflow, then the flow from a particular segment is basically linearly related to the number of vehicles in that segment. So it keeps increasing with the number of vehicles until it reaches some sort of saturation point. Now, if there is congestion, then it takes the form of this red curve, which is R here, Ri. If there's no congestion, it takes the form of this green curve. So when you look at this Ri, what it says is that the traffic is going to be flowing at maximum capacity until there is congestion, at which point this is going to keep decreasing, and then there is going to be standstill at this point where it meets the x-axis. So basically the traffic flow in or out of a particular segment is going to be the min of these two quantities. So it's going to be the minimum of Si and Ri plus 1, where traffic is flowing from cell I to I plus 1. So when you put all of this together, it basically gives you a piecewise affine dynamical system, which is hybrid because there is continuous traffic flows and there is discrete things like traffic lights and ramp meters. It's piecewise affine because these flows, inflows and outflows, are basically affine, as you can see in this graph on the right. And basically it's a dynamical system because traffic is, the patterns are changing with time. So the more critical thing here is that this kind of captures the change in the way traffic flows are going to behave depending on the congestion levels. Like I said, the traffic flows are going to be the min of these two curves, the green one and the red one. So the red one will take over when there is congestion. So basically this system itself is going to be changing in behavior as you change, as the congestion level changes. So this can capture quite a lot of complex patterns. For example, in the I-210 example I showed you, this can capture things like shock waves of traffic, which are basically congestion wave patterns that repeat over time and emerge kind of organically. So this is a little bit more detailed in terms of capturing the traffic behavior. Now, from the perspective of putting this model into an optimization problem, a nice thing here is that under some conditions, this model actually has what are called monotone flows, meaning that if you take the flow, the net flow of traffic at a particular segment, it's basically monotone in the density of the traffic in that segment, as well as monotone in any additive uncertainties that go into this system. So this is super useful from an optimization perspective, because then we're dealing with monotone constraints. So monotone means that as the density increases, this function is also going to increase, and vice versa. So this actually holds under some very mild assumptions on the traffic flow. Okay. So like the previous thing that I talked about is basically a data-driven approach to directly forecast these flows that we can use as future data or look-ahead information. Now, there's also a way to basically use the data, historic data that we have, to fit this particular hybrid piecewise affine model, and then we can use this model as a simulator to get future predictions as well. So this is the second approach here, which is a little bit more analytical. It is still data-driven, but basically it gives you an underlying analytical model with some uncertainty quantification. So when we look at this here, essentially we start again with traffic data. So we can start out with traffic volumes and basically ramp metering or traffic signal values at particular locations. And we compile all of this data just like we did in the other case. And we can learn parameters of this particular model, of course, while satisfying things like, of course, the traffic flows have to be positive. You know, these are physical constraints. States are continuous, meaning that you can't have vehicles sort of disappearing and appearing in between different cells. And then, of course, finally, for optimization purposes, if we're using this model, we would like to impose this monotonicity thing, because this is a huge benefit when we're solving optimization problems where this is going to be a constraint. However, the challenge here is that actually if I'm given a data set that looks like this on the left, it's very hard to understand where the dynamics are going to change from free flow to congestion. And basically because that itself depends on the particular traffic densities at each location, finding out when this system is going to switch between different congestion or free flow modes at different cells is a very complicated problem. Also, this data is very high dimensional, and we're trying to fit a very high dimensional sort of a piecewise affine model, which is in and of itself a challenge. So the first thing that we do here is to just to give a high level idea. It's a little bit complicated, but what we can do is use some sort of clustering technique using machine learning or various other clustering techniques which are a bit more specialized to this problem. One of them is listed here that we specifically used to basically look at different sort of combinations of cells and see which of them are going to be congested or free, and then it basically gives you a list of modes. So let's say we have 3 cells in our network. It could be all 3 could be free flow. There could be congestion in the last 2, and the first one could be free. All of them could be congested, and there's like a whole list of possibilities. So we can basically cluster this data to see which of these data points corresponds to which of these particular modes. And within each mode, we will then go ahead and fit this sort of affine traffic flow model that I talked about to capture the dynamics of the traffic flow. But then what we would end up with, in this case, let's say there are 3 modes that we encounter, you would get 3 different affine models. So each of these 3 different affine models can be used to predict the traffic dynamics if there is a particular mode that we're in, a congestion pattern that we're in. So what this basically does is it gives us a way to predict these traffic flows in a little bit more systematic fashion. In the interest of time, I'm going to skip sort of the details of how this is done. Basically, we have results, it can be done. But I'm just going to go back and zoom in on what it means going into this, right? So I said that this solving this problem requires some look-ahead information on the traffic and on the way EVs are going to drive and how long they're going to spend in this segment. And we can either use the data-driven approaches like the neural network time series type models that I talked about earlier, or combine it with something a little bit more rigorous like the cell transmission model here to better estimate these traffic patterns. And then what we would end up with if we're putting these dynamics in here is a set of monotone constraints. From the grid side, there are also constraints like the power flow equations, voltage and frequency constraints, and so on. If you're considering AC grids, we haven't thought about, put in all of that yet, but this problem can get potentially pretty complex. And these are the kind of questions that we're kind of working on addressing now from the electrified roadways. So if you want to take this from a simple case like this to all the way to a practical setting where we have everything ranging from grid constraints to traffic dynamics that are impacting the charging on these roadways. So I'm going to stop there and hand it over to Junjie to conclude.
Well, quick conclusion. We have this electrified traffic flow connect both systems. We demonstrate a couple of examples where indeed we can optimize that by optimizing electrified traffic flow. Indeed, we can improve the performance of both systems. There are a lot of things that we're working on and a lot of directions we're interested to explore and potentially working with you guys. So let us know if you have questions or any feedback.
All right, thank you. So the last portion here was carried out by one of the students that's working with both Professor Junjie and myself, Yifan Dong. So I just want to mention that. And he's funded by Aspire.
Very good. All right. Well, very interesting. Thank you. I know we're a bit over time, and so feel free for those that may need to step out. But I would like to still give just a moment for those that are able to stay, and we'll continue the recording. Thanks again for those that were able to join us today. But if there are any that are able to stay on, I would like to give you a chance to ask a live question or two. Any questions before we sign off for Siva and Junjie?
I have a quick one.
Please.
How, I mean, you guys were saying that the clairvoyant optimization problem is convex, but are all the other ones convex too?
The other ones, you mean for the first two parts, or
Yeah.
maybe Junjie can take that?
Well, that would actually get into a lot of details. I think the first problem by itself, it is not a convex problem because the decision variable is not a finite dimensional variable. It's a function, and there are a bunch of equilibrium constraints. The second one actually turns out original formulation is not convex. We're able to identify a convex problem to solve that, and we can show the solution of the convex problem is actually solving the original problem. Yeah, for both, they are non-convex by itself.
Thanks.
Great. Thanks, Liam. We might just take time for one additional question if anyone has one. All right. Well, I think we've given everybody a lot to think about. Anyway, interesting work. Appreciate all the efforts here within Aspire. Definitely an important perspective for us to be considering. I think it's an interesting way of framing the problem, and kind of reassuring, as you've stated, that we don't silo off our considerations. And I know, at least on my side in particular, we're really focused on minimizing cost of electricity, showing that this doesn't have to be so expensive. These are all good reminders. That's not the only thing. So let's look at this as a system. All right, really appreciate it, Siva and Junjie. Thank you for taking the time. I know it's late and getting later for you this evening. So appreciate you joining in and offering this lecture. We'll let everybody sign off.
Yeah, thank you so much for the opportunity, and very nice meeting you guys. See you.
Bye-bye.
Great. All right. Thanks again. We'll see everybody. Bye.